So in this last two lectures, we have seen graphical method and bisection method. There are still 4 more methods that we'll work through. We started doing bisection where we started computing the value of x after each iteration. So I want to introduce some terminology which will make our discussion much smoother. So when I write xi, I'm referring to the value of x after or at the ith iteration. Okay. So when we talk about, say, you start with a guess value and then you make it more and more refined as you go through iterations, the absolute error is defined as the value of x from the next iteration to the previous iteration. Or if you call this current, this is your next. You call this current, this is your previous. Look at it both ways. So this could be current. That would mean this is next. Or if you see this as current, that would be previous. So that is just the difference between the two values. Obviously, it will have a sign. And there is no universal rule that it has to be defined this way. You might define it as xi minus xi plus 1, which is perfectly fine. But for consistency's sake, since we are a class of 37 people, we'll just stick to this. But I don't want to give you the impression that this is the only right way. Okay. If you sometimes consider the absolute value or only the magnitude of the absolute error, that will be only a positive number because it's just a magnitude. But generally, absolute error can be negative or positive. Relative error is the same thing except it's expressed as a percentage 1 minus xi plus 1 divided by xi. That is compared to the previous iteration by what percentage my current value has become closer. That's what we are going for here. It should be defined. Yeah, this is correct. And then tolerance is a value that we choose. That is, if we want our convergence to happen such that the two values don't differ by each other by a lot. By lot meaning, like, let's say they are within 1% of each other, we'll choose our tolerance to be like 0.01 so that the number of iterations will be necessary to get the relative error to be less than the chosen tolerance. Okay, and we'll see these through examples. But what I want you to take away is this these 1, 2, 3, 4, 5 concepts that we'll retain from here on as we discuss iterative methods. Okay. The first method we saw, graphical method, it's sort of the most intuitive. You have to graph the function and literally find where the curves intersect both the left side and right side, and you can narrow down the possible point of intersection. I always recommend to use graphical method to be used as a precursor to identify where the root or roots may be found. And then the remaining 5 methods, okay, you can use them to hone in on the root to a desired degree of precision. And within these two sections, that is, I label them as bracketing methods versus open methods. Can you recall bisection method? How did that method actually work? Can you recall that? And somebody can say that in a few simple words. How does the bisection method work?
Basically, you're looking at your values and the difference between your left hand versus your right hand side. And whenever there was a positive sign versus negative sign, mean that there was a root between that. And so
Whenever the sign flips from positive to negative or negative to positive, that means the functions must have crossed each other. So if you had two curves, say suppose you had this is your left side and this is your right side and this is your root. Until you approach if you approach the root from the left side, until then the left hand side was greater than the right hand side. So if you define absolute error as LHS minus RHS, then in this region, can I say epsilon A will be positive in sign? Is everybody cool to say that? Yes, no? If you are saying no or thinking no, you should say that to me, not just convey it through your face. Because if I read your faces, I can see some no's, but if I call them out, that would be like I'm putting you on the spot. I don't want to do that. You repeat the question that you asked. The question is, if the left hand side, suppose your equation that you want to solve is this. This is the equation you're trying to solve, okay? And let me draw graphs that actually look like these functions so that the discussion is clearer. E power minus x looks like this. Okay, and say x, the curve x looks like this. So this is left side, this is right side. We are good so far. If I define my epsilon A as being LHS minus RHS, to the left of this point, this is my root, to the left of the root, epsilon A will be greater than 0. Would you agree with that? Because this curve lies above this curve. Yeah. To the right of the root, epsilon A becomes negative because now the right hand side lies above the left hand side. If there is a sign flip, that means a root must exist somewhere around here. That is, you went from here to here. So here it's positive and here it's negative. It means in this interval there must be a root. That's what the bisection method is about. Are we now together? Right? You don't have to go from left to right. You could have gone from right to left, where it went from negative to positive. It still means the same thing. Okay? These type of methods that kind of find a range and then you tighten your screws until you narrow and narrow and narrow and get it to a certain precision, those are called bracketing methods. You put a bracket and then squeeze it until you find the exact root. Okay? Does that make sense? The word bracketing means finding a range and then narrowing down until you get it figured out. There are other methods which are called open methods where you just need a guess value. You don't need to specify a range. There is to make bisection method work, you have to specify a starting value and an ending value for the range where the root may lie. Our root is lying, except you have to find out where it is. Open methods. So I'm going to write here bracketing methods. Bracketing methods require the specification of a range x1 to x2 within which the root is expected. Within which the root is expected. Open methods, we are going to see them today. Open methods require only a guess of the root and are designed to take you to the root. I'm not writing like they would write in a textbook. I'm writing like I'm actually talking to you. So don't pardon this, take you to the root. Now, one thing you should remember when you use these bracketing methods is that if you wrongly specify the interval, it will take you farther and farther away from the root and your solution will never converge. Suppose the intersection happens here. By some mistake, you thought x1 is here and x2 is here, and in this range it is positive. The epsilon a is always negative both here and here. If you specified this as your range, you might do 100 iterations or whatever, you will never converge. Okay. So the prerequisite for using bracketing methods is that you have to be absolutely sure that this range contains your root. If it doesn't, it will not converge. Okay. So this false point method is supposed to be a method which converges faster than, say, bisection method. First, I want you to tell me, when I say a method the third method converges faster than the second method, what exactly do you understand? I want you to speak.
Meaning having less iterations between.
In fewer iterations, that is, it gets you to the answer in fewer iterations. So if I draw.
Did you start recording?
Yes, I did. Thank you. At least one person is here with me. Thank you, whoever that was. So if I plot the relative error, okay, recall what is relative error? Relative error is 1 minus next divided by previous as a percentage. And then this is number of iterations. If I say bisection method converges at a certain rate, okay, so let's say this is bisection method. And by convergence, what I mean is the relative error is dropping. Initially, the relative error, let's say, is like 100%, then it drops to like 50%, then it drops to 10%, then it drops to 0.1%. It keeps dropping. That's what I mean by after each iteration, the error keeps reducing. That means you are getting to the correct answer. When I say something is converging faster than the other, what I mean is precisely this. I am able to get to the same outcome in fewer iterations. So, same outcome in fewer iterations implies faster convergence. When you use a numerical method, you want accuracy. You want the correct answer first of all. You not only want correct answer, you also want to be the first person to get the correct answer. If you are four of you are writing programs with 4 algorithms, you want your program to run the fastest, assuming all of you have equal computing power. It means you have to choose a method that converges in fewer iterations. That's what he said, right? So false point method is supposed to be an improvement on the bisection method in the sense that it will convert faster to the answer. Okay, so let's try that. Okay, we'll try the false point method before we start looking at these other methods. Any questions before we start an example? No? Yes? Yeah, sorry. Put this. Good. So then let me first explain to you what this false point method is about. So suppose you have a function, okay, f of x, and you're trying to solve the roots of f of x equal to 0, okay? And you have x. If f of x looks like this would be your root. We'll call it xr. Okay, this would be your root. We'll call it xr. And suppose we have identified an interval which contains the root. Suppose this is x1 and this is x2. The interval x1 to x2 contains xr. We have identified that. How would you identify it? By tracking the sign of f of x. It should have gone either from negative to positive or vice versa. Okay, so we have identified x1 and x2 contain xr. Okay, now if you just take these 2 points, what is the value of the function here? This is f of x1 and this is f of x2. It's easy to figure out since you know f of x. Suppose f of x were something like x e power minus x plus sine 4x equal to 0, something, for example. You can draw a straight line that connects these 2 points. You can draw a straight line that connects these 2 points. It will intersect the axis at some point. Okay, we'll call it, say, x dash. Knowing some algebra from before, even if you can't look at it and say the answer, can you at least agree with me that you can work out what x dash will be? I'm not asking you to tell me a formula, but can you at least know how to get there? This doesn't look like Greek and Latin to you. That's what I'm making sure. Okay, good. So now we'll actually write down that. So you have 2 points, x1 and f of x1 and x2 and f of x2, right? You have 2 points, they are joined by a straight line. This point is joined with this point. How will you write the equation of the line defined by 2 points? You will write y minus f of x1 divided by f of x2 minus f of x1 equal to x minus x1 divided by x2 minus x1. You have seen this before, right? This is just algebra or geometry, whatever you want to call it. Now, our x dash is the point where what is special about x dash?
It's supposed to be.
By definition, you don't know that where the root is. So not with respect to the root, but if you look at x dash on this graph, what stands out about it?
It's f(x) is 0.
Its y value is 0, right? Okay, x dash is the point where y equal to 0 or y dash equal to 0. So I can put 0 minus f of x1 divided by f of x2 minus f of x1 equal to x dash minus x1 divided by x2 minus x1. If you remember this picture, swear to God, you don't have to remember this formula. And if you are actually, you know the concept of the two straight lines defined by 2 points, you can write down this, you don't have to remember this, that's what I'm saying. Rearrange this to get what is x dash. X dash is x1 minus x2 minus x1 divided by f of x2 minus f of x1 times f of x1. I'm just rearranging this.
Multiply by 4.
Yeah, all I did was to take this to the other side, put x1 on the other side and. Okay. So you are keep recalling x1 and x2 is the range containing the root, which we have called xr. Okay. So you are now saying an estimate for xr may be obtained by successively using the formula for x dash with the range suitably narrowed. Write this down and then I have a question waiting for you. So you can keep using this formula to successively get the next iteration values of x, but you have to keep narrowing this interval closer and closer. So suppose, put your pencils down once you're writing, put your pencils down so I know that you are listening. Some people are still writing. Okay, put your pencils down. Suppose the way I've drawn this, you figure out x dash. It will be some value greater than x1 but less than x2. The way I've drawn it, what would be f of x dash? Louder, please.
Negative.
It would be negative the way I've drawn it. Okay, it would be negative, whereas f of x2 is still the same positive value. So that means I have now a different point from which I can connect two straight lines. And now I don't want to call it x double dashed or whatever. I'll now start calling this, say, I've already used 1 and 2. X dash, for lack of a better terminology, I'll call it x double dashed. The point being, I am getting closer to the root where at one point I will start seeing that f of x double dash or triple dash or quadruple dash will become practically 0. That's when I know I need to stop because I've almost approached the root. Okay, so let's do this now as an example and you will see it in action. Okay, let's try to solve. We find an example here from the book. So we'll do x minus e power minus x equal to 0. That is our f of x. Okay, we'll do that as an example. So I'm going to do this like a table, which will be easier if you start following it. So this is my suggestion. Please follow this table. Step 1, iteration number. We start with the initial guess for the range. We'll call it iteration 0. Okay. What is our function? Our function is x minus e power minus x. What is f of 0? Minus 1. And what is say f of 1? It's something positive. That is 1 minus e power minus 1. That is a positive number clearly. So we can say 0 to 1 contains our root. 0 to 1 contains the root xr. Okay. So we'll say, I call it x left and x or x lower and x upper. X lower is 0, x upper is 1. Okay. So now we'll write x I plus 1. This will be I. This is I plus 1 using our formula right here. This is equal to x lower minus x upper minus x lower divided by f of x upper minus f of x lower multiplied by f of x lower. Just 1 second, I'll get out of here. Zero, zero, or 0.00, 1.00. And now I is 0. So this is current, and this is sort of like next. Okay. So what is x1? Use that formula and compute x1. Go ahead, do that. So I'm just going to write it out. You can punch it in your calculator. X lower is 0, 0.000 minus x upper is 1.000 divided by what is f of 1 and what is f of 0? F of 1 minus f of 0 multiplied by f of 0. So while you get ready, I'm going to start an Excel sheet to do this problem. Right. So what I figure is before this column, it would be convenient if you had f of x lower and then f of x upper. If you had two more columns, it will be convenient. All right. So now I'll rewrite this. I'm going to share my Excel sheet with you so you can also see this on the sheet. F of x lower, f of x upper, and then xi plus 1, which is according to a formula xi minus x upper minus x lower divided by f x upper x lower times f of x lower. My Excel sheet says f of x lower is minus 1. And what is the f of x upper? 0.6321. We'll leave it at 4 places. 0.6321. So then, what would this be? x1 equals xi or x lower, which is 0 minus 1 minus 0 divided by 0.6321 plus 1 multiplied by minus 1. Please evaluate that and keep it ready. What are you getting? You're getting 0.6127. We'll wait for few others also to get this 0.6127. Okay, is everybody generally getting this? If you are not, it could be because of punching numbers incorrectly or making a mistake in the formula. It can't be, there are not too many possibilities. All right, so now you have 0.6127. Now listen, please listen. You need to first figure out, of course, 0.6127 is between 0 and 1. You need to figure out is the root to the right of 0.6127 or to the left of it. What happens if the root is to the right of this number? So first thing you want to do is next is to calculate what is f of xi plus 1. That's the next thing you should calculate. So do that. Compute what is f of xi plus 1. That would be x minus exponent of minus x with 0.6127. There is first column, second column, third, fourth, fifth, and sixth. If you punch in 0.6127 into this function, you will get something like 0.07 something. Do you? 0.0708. 0.0708. Now tell me, this is positive, this is positive, this is negative. Is the root to the left of this number or to the right of this number? If I draw it, it will become obvious. I need someone to say what they think. Is the root to the left of 0.61 or to the right of it?
It's a lot, because we can see that it's trending upwards. It's not going.
See, these two are of the same sign.
Yeah.
These two are of the same sign, which means the root is between this lower and this value. Right? These two are both positive. Right? So now what that means is your lower becomes, and your lower is still 0. Your new upper is 0.6127, 0.000. Now repeat this iteration. What is f of x lower? Still -1. What is this? This is 0.0708. Now you compute what is x2, which is based on x lower, which is still 0, minus 0.6127 minus 0 divided by what is f of x upper? 0.0708 minus of -1, which is +1 times -1. Compute this, please. Compute this, please, and tell me, and also the function value at that point.
0.5721.
0.5721, that's correct. Point. I'll say 0.5722 rounded to 4 decimal points. And the value of the function?
0.0079.
0.0079. Thank you. You can just take a minute and see this. Your root is now, or you're getting towards 0.57 something. And look at your function value. What is the ideal function value if this were a root? We're trying to solve f of x equal to 0, right? Ideally, this should be 0. If it's 0.000 and something, that is to within 3 decimal points, it's practically 0. So we are down to 2. Let's do one more iteration. So now before you do that, this sign is positive. So is this, which means what? You would still retain your lower, but replace this with the new value of upper. That would be 0.0000. This is the second iteration, 0.5722, with this value being -1 and this value being 0.0079. So now you can compute x3. I won't write the formula. You put it here and you tell me the answer. So, in the interest of time, I will just say my x3 value or my x3 value is 0.5677. 0.5677. 5677 and my f function value is,
0.0009.
yeah, 3 zeros and a 9.
Yeah.
0.0009. Some people can just say, for my application, this is good enough and stop right here. I have figured out the root down to or within like 4 decimals. Okay. You could do one more iteration, but at least you know, you understand the process going on here, right? So let me bring my Excel sheet. So those who are inclined to programming, here is a small challenge for you. Please listen. No need to write. I started with iteration number 0, lower, upper, function value, and then the value of x in the next iteration, and the value of the function. I got 0.07. What I've done here is just manually say my lower is same as the previous lower, whereas my upper is equal to h3, this cell. I manually have done this. Just say equal to h3, like manually putting it. And then if I use 0.6127, I get the second iteration 0.5721, and I manually put it here. Third iteration 567703, and I can do a fourth iteration, which is just same lower, but upper being this, and my rest of the values being the same. I'm converging to within 9 times 10 power 5. We can keep doing this. Now here is something you could try. This is already online. I want you to write if statements. Use if statements to see the value here and base your lower and upper in the next iteration based on these values. Do you understand the problem? You have a flowchart. If this were positive, then the lower carries over, the upper gets replaced. If this is negative, the upper carries over and the lower gets replaced.
Replaced with the new.
Replaced with the new value. I want you to use if statement, if and then statement, if then statements in Excel to fully automate this program. This is sort of semi-automatic. I'm manually punching these values. I want you to fully automate it. Can you try? Not now, but I want you to try at home. Okay. Does the method make sense to you? Okay. So we'll have to move on to the next technique because we have a few more things to see. But I want you to try 2 things. One is I'll add notes here. Fully automate this this calculation using if then statements. Oops, I want this equal to. Okay. The next thing is do the same problem with bisection method and compare which converges faster. Hint, that would be the false point iteration method. Also, fully automate your bisection calculation as well using if then statements. If your goal is to pass the course, do well in your exam, get a grade. If you just do number 2, that's okay. At least you learn something. You want to become an engineer, do everything. try to use Excel to do this automation. Okay, I'm sure you have used if then statements in Excel. So just put it to use. All right, good. Any questions before we move to the next topic? All right, so then. To take it away. So these two methods, the bisection method and false point method, both need you to guess the range where the root may lie. And for that, I want you to use the graphical method as the first step. If we want to go for methods that don't need you to do the range selection, but just give one initial guess, those are called open methods. And there are 3 of those that we'll learn. The first one, section 6.1, is called fixed point iteration. 6.1, fixed point iteration. I'm asking you to self-study this. There is a reason why I'm asking you to do that, because 1, it's actually a very easy method, and 2, it is very related to the false point iteration we just saw, so you would be able to easily connect it. So I don't have to spend time. I want to focus on Newton-Raphson, which by far is the most useful technique in my opinion. I use it all the time whenever I need to solve such equations, because it's the one that works almost all the time. Okay. 6.2, Newton-Raphson iteration method. So suppose we want to solve f of x equal to 0, where f of x is a differentiable function okay, then Newton-Raphson method. So if you think about f of x and its root, Newton-Raphson method works by writing xi plus 1. So just 1 second here. Xi plus 1 equal to xi minus f of x or f of xi divided by f dash of xi. It's like almost using this graph and a guess value. Suppose your guess value is here, say xi, okay. If you want to get a better guess and say call it xi plus 1, that is to go towards the root, okay, by writing f dash of xi equal to f of xi minus 0 divided by xi minus xi plus 1. This is like saying xi plus 1 will lead us to the root. It is like saying it. So with that assumption, you write the equation or the expression for the derivative or slope and rearrange it to get this formula. The formula is not like it will directly lead you to the root, but in successive iterations, you will approach the root closer and closer. Okay, so we did that problem, right? F of x equal to x minus e power minus x, and we want to solve f of x equal to 0. Now try that same problem using this method. same problem. You don't have to guess the lower and upper, you just have to make a single guess as a starting point for the iteration. And you know the root is somewhere closer to 0.567. So just to keep it sort of real, don't guess that. At least in this situation, don't guess the root itself and say I got the answer in like one iteration. Don't do that. Let's say our guess value is 0. We'll start there and see what happens. I'm going to write this here again like a table. So I have my iteration number, we call it I. I have my xi, the initial guess. I have my ref of xi. I can calculate f dash of xi. And then finally, I can calculate xi plus 1 equal to xi minus f of xi divided by f dash of xi. So what is f of x? This f dash of x 1 plus e power minus x. So my guess value, 0th iteration, I'm going to guess it to be 0. What is f of 0? F of 0 is minus 1. What is f dash of 0? Put 0 here, I get plus 1. Right? So my x1 is x0 minus, what is f of this is minus 1 divided by plus 1. And what is my x0? So my x1 is 1. Why don't you do 2 more iterations? I'll develop a program that I can show you. Oh, I think I made a mistake. This is 2. Thank God for Excel, right? So this will be not 1.0, it's 0.5. So I can write out the numbers that I have on my screen, or I can actually show you the screen. Let me do the second. Is everybody able to get up to 0.5? Yes. So in the 0th iteration or the initial guess, we guess 0 and we compute the corresponding value of the function and its derivative. And just to keep it organized, we'll say f of x equal to x minus exponent of minus x, and f dashed of x equal to 1 plus exponent of minus x. So that later it makes sense to you. So you have f of x, its derivative evaluated at 0, and then the value of the x or the value of the root at the next iteration. So you get from 0 to 0.5. So the value of the root is around 0.567 something. Okay, so in just one iteration we have gotten up to 0.5. Second iteration, you start with 0.5, you further refine it to 0.566. By third iteration, you get 0.567, which after that, but just by the third iteration, your function value is dropped to within 10 power minus 6. Already it's very close. Just 2 iterations you are there. Contrast that with, so I'll add a note here. Compare the number of iterations to convergence with number 1, your false point method, and number 2, false point method and bisection method. So I want you to figure out the number of iterations for the false point method, which might have been 3 or 4. And for bisection method, it might be a few more, maybe 5 or 6, and record it here so that you can actually have a nice comparison. Okay. So if we say, when you say number of iterations to convergence, before that you have to define what is convergence. Convergence is f of x dropping below 1e minus 6. That is what I'm defining as convergence. If I go by that yardstick, I can get there in just 3 iterations here or 2 iterations here, whereas you might need, actually you might need 1 more iteration. Not even 1 more, actually 2 more iterations. I said less than 1e power minus 6. So we have to go even more number of iterations. So this 6. So you need 6 iterations to go below 10 power minus 6 using false point method, whereas we need only 2 iterations to accomplish the same thing using Newton-Raphson method. Just by the second iteration, it's already below 10 power minus 6. That's what I'm trying to show. To add to this, if you also add bisection method, we had a different example back then, but you will actually be able to say how many iterations does it take for each of these 3 methods to get you an answer with the same precision. That is the convergence rate. Okay. Any questions before we do another example? Yes.
So you're saying that to get below 10 to the minus 6, and so for the Newton one, it only took 2 iterations, but for false point, it was to 6.
6.
Okay.
Yeah. Now that we are on a roll, meaning you have done the same problem using two methods and you will do the bisection as a like a homework or practice. Let's do the same problem using one more technique called secant method, so that we have a comparison. And next lecture we'll just do examples from each of these and go forward.
I don't know.
Yes.
10 to the minus 6.
That is just something I selected for my hypothetical application. You might choose 10 power minus 9 or only 10 power minus 4. That's up to the person who needs the solution done. So speaking of examples, today is 5th, right? On September 12th, that is next Tuesday, I wish to hold a 1-hour recitation or problem solving practice between 1 to 2 p.m. It's optional. You don't have to attend. You're welcome to attend. We'll record the examples we do on the board and we'll put it on the web page. Okay. It's just for me to just do more practice problems with you. Remember, the homework has only one problem to be done by several techniques. That is not enough practice. So if you just do that one problem, got full score on your homework and show up at the exam all with your chest puffed up, that won't work. That won't go well. I'm telling you right now. Okay, so either with me or on your own, please practice a lot. Right? All right. Next technique, secant method. Put this up. Don't be surprised. The exam will be hard because I'm also giving you a makeup exam possibility at the end. Don't expect an easy exam, telling you right away. So we saw Newton-Raphson, right? Which is getting a function, say if you have f of x equal to 0, it requires, Newton-Raphson requires that f dash of x be easily calculable. That's not always the case. Some functions are very long and tedious to evaluate. So we need a technique that is just as good, but does not involve computing the first derivative. Okay, and that method is called section 6.3, the secant method. The secant method is actually very, very intuitive for you to understand. I'm just going to write xi plus 1 equal to xi minus f of xi times xi plus 1 minus xi divided by f of xi plus 1 minus f of xi. Now drop your pencils and please answer this for me. Doesn't this look familiar? At the start of the lecture, we saw the same equations as being called false point method. What are we doing here? I'll write also the formula for false point method. The false point, please listen, you don't have to write, I'll give you time. The false point method was a bracketing method, meaning you have to narrow down a range which contains the root. The secant method is the open method. The open method, and you don't have to, not necessary to find the range containing the root. Containing the root. Okay. This method will have, as you will see by demonstration, you will have faster convergence than false point or other methods, but can also diverge if the initial guess is poor. We'll see an example like that. Guess is poor. So for all problem solving in this unit, as well as whenever you use any approximate method, I recommend checking by back substitution in the original equation. You need to, if you figure out the root is like 0.567 something, you need to put it back into the original equation to show actually it satisfies the equation. That's the last step in your process. You have to always check before you sign off something. Okay, so this has to become part of your thinking. You choose a method, you see the equation, choose a method, get the answer, put it back in your equation, check it before you say, yes, I'm done here. Okay. Let's solve the same problem using the secant method. And let's start again with an initial guess of 0. We'll see what happens. So, in terms of your iteration, you have x, you have f of x, okay. You are going to calculate xi plus 1. Wait, hold on. Oh, sorry, this is not I plus 1. This is I minus 1. Previous iteration. So your formula is xi plus 1 depends on xi and the previous value of xi minus 1 as well. So you have to guess your starting value of, let's say, x0, we'll call it 0, and x minus 1, we'll call it 1, or we'll take it 1. Now you can start computing x1, x2, up to convergence. So if xi is 1, what will be f of xi? Where f of x equals x minus e power minus x. That's your 0.63 something, right? 0.6321, thank you. 0.6321. 0.6321, and for that we don't have a next, and then when you have 0, that is 1. Oh no, that is minus 1, and now you can compute what is x1, which is going to be x0 minus f of x0 divided by f of x minus 1 minus f of x0 multiplied by x minus 1 minus x0. Let's plug in the value. What is x0? 0 minus what is f of x0? Minus 1 divided by 0.6321 plus 1 times x minus 1 is 1, 1 minus. What is this value? 0.6127. And also we should ask, what is the value of the function for 0.6127? So I'll write f of xi plus 1. What is that value for 0.6127? Would be 0.6127 minus exponent of minus 0.6127.
Negative 1.2327.
1.2327. Are you sure?
Oh, I forgot the negative in the exponent.
Yep.
0.070.
0708. Now compute x2. What will be x2? X2 will depend on x1. X2 will depend on x1. It will also depend on x0. Right? It's going to have x0. So that is going to be minus f of x1 divided by f of x0 minus f of x1 times x0 minus x1. I'm going to pull up my Excel sheet. So iteration. So let me bring up my Excel sheet and let's do this together so that you can see the steps. I'll give you the last 5 minutes to just write down everything. Okay, so let's focus on this. Iteration. We need the value of x, xi, and then the value of the function f of xi, and then the value of the xi plus 1, which is equal to xi. Can somebody repeat the formula for me, please? Yeah, xi minus f of xi, thank you, divide by f of xi minus 1 minus f of xi, close bracket, close bracket, and then I have to multiply this by xi minus 1 minus xi. All right, and then I'll also write and also compute what is f of xi plus 1, because that's what I need to keep checking. This needs to go below the chosen tolerance of 1e minus 6. We are all together at this point. Can I do the first iteration? Actually, I should do the -1th iteration, which I'll say 0, and then the 0th iteration, which these two are practically guess values. Okay, guess. And what is f of 0? This is x minus exponent of minus x. So for the sake of completeness, I'll copy this and put it here. So this is x minus exponent of minus x. All right, so now help me punch in the formula equal to, I start here, equal to this value minus, what is f of xi? Can you tell me the cell number? E4, okay, good. E4 divided by E3 minus E4, wouldn't you agree? The denominator. F of xi minus 1 minus f of x. E3 minus E4. E3 minus E4 times, what will be the numerator? D3 minus D4. Right? D3 minus D4. D3 minus D4. Enter. 0.612699 something. And then I also have to evaluate the value of the function, which is x minus exponent of minus x. 0.0708. Already we are within 110. Already within 0.1, just in one iteration. Now, the place where false point method and secant method differ from each other is here. When you evaluated the value of the function, in false point method, you adjusted it to narrow the interval suitably, whether the root is to the left of it or the right of it. Here, in secant method, we'll just automatically use this. We won't care to check whether the root is still contained or not. That is what gives the secant method much faster convergence than the false point. But it also gives you the risk that it could diverge, because what happens when you fall out of the range, you will go somewhere away and away and away. So let's do further iterations. Iteration 1, what is xi? Xi has to be this now. It is automatically this. Okay, and f of xi I can copy paste. The next iteration 0.563, value of the function within 2 decimal points. We are there. Okay, within 2 decimal points. Then second iteration or 2. This is equal to this value automatically, no questions asked. And the value of the function I can copy. And the root is getting tighter. We are within 10 power minus 4 in 3 iterations, still reducing. So let's do one more. I can just keep dragging this down. This is satisfies the convergence criterion. We are within 10 power minus 6, which we chose for this problem, and we are there in 3 iterations. Okay. The key thing is when you are trying to build like multi-step routine, that is, suppose you are solving hundreds of such nonlinear equations in every iteration as part of a much bigger task. You want speed, that's why this is important. But you also don't want this to get you away from the root. Okay, so you have to take this answer and do back substitution within your problem to see if it actually works. Okay, that is a really important step. Okay. So to your homework or suggested homework, I'm not going to evaluate this. Also try secant method. Okay, so this Excel file is already there. If I close this, it gets saved and I'll upload it right now. So I want you to try this. Okay, yes.
Can you go back to the other one?
Which one? Oh, the one. Yeah.
So, how did you get -1 and 0.
Yeah.
Side -1.
Oh, you mean these two guesses? Yeah, that I didn't think too much. I just took my my false point and then just used it. You are welcome to try different initial guesses. And you can see most of the guesses will lead you to the answer except when it doesn't. So there is no universal correct. Okay. All right, so. Yes. Yes.
Are we not counting that negative 2 from 0 to 0?
No, I don't. We automatically take this and use it as the next one. We do the accounting for the negative and positive, that is the false point method.
Okay.
Secant method does not care about the sign.
Okay.